and you would choose the login node. Okay, so that's in the slides as well. So you should see something like this and click start on login node. Hopefully that works. Sometimes it can take a while because there's so many different people trying to log in at the same time. Once you're here, you can open a terminal uh, and try making this bigger. Okay. If you don't like this, you can also just go into your own terminal, SSH into Perlmutter, and do it the same way. Hopefully nobody is having issues logging in. But if you are, actually, I forgot to mention, Cornel is around to help, and Steve is also around to help uh, in case you're facing issues. Oh, and Wahid. Okay, so we're just going to go through the README and do this step by step. First thing is to clone the repository. I've already cloned it, I think. Yeah. Um, and CD into the repository. We're going to be using a training account for this tutorial, but if you want to run this afterwards, you can use your own NERSC project accounts. If you don't want, you can also apply for computing time. We will be using a reservation to access the set of GPU nodes that we have reserved for you. But if you're running it outside of this session, then you would just remove the reservation flag and you'll be sent to the normal queue. In terms of the Python libraries, we don't have to install anything. We've already created a container for you. This is a Docker container. It's built on top of NVIDIA's cloud containers. You can click at the links here to find out more about it. So NGC is NVIDIA's GPU cloud containers. These are optimized containers specifically for deep learning workloads. They keep releasing one every few months, and we will be using the 2408 container for this training run. We can go through the model and data if you'd like again. So once again, we're doing weather forecasting. The point is to emulate this process. This is like total column water vapor over the entire Earth, and you want your vision transformer to emulate this entire process. If you're interested in looking at like the network implementations, you can go to network/wit.py. And in general, if you're interested in how the data set works, we've also linked the data and things like data loader. If you want to go into it, you can. And one last thing before we start is that we are managing configurations using YAML config files. Those of you who are not familiar, YAML is a way to manage your configurations. So if you go into config and with.yaml, what you'll see is all the hyperparameters that we're using to do our training runs. We recommend you use some sort of configuration manager, such as YAML for training runs, because it gets very hard to track exactly what you used for different experiments. The way this works is you kind of define hyperparameters like embedding dimension, depth, training configurations, your data, and then you can kind of inherit from that base configuration and keep changing whatever parameters that you like. So for example, the shot configuration is inheriting from the base. It's just limiting the number of samples so you can go faster and so on and so forth. There's like multiple configurations, and the goal is to run every single configuration using varying number of GPUs to see different performance characteristics. Okay. Okay, so let's get started. So the first thing we're going to do is we're going to submit a short configuration. This is just for you to see some simple things that I was talking about in the last few slides. These are like optimization tips, flags you want to keep on to get performance, good performance on a single GPU before you move to data parallel scaling. So if you just copy that and submit it, I can't remember if all this. It will submit that job to the batch scheduler. So um, for Perlmutter, we use the batch scheduler to which basically maintains a queue of jobs. So we're not going to be using any interactive nodes here. And if you just type SQUE minus E, which is my username, then you can see that I have this job that's running on this partition and is using this node. Okay, so is everybody able to submit that job? Okay, actually, anybody not able to submit that job? Okay, good. Okay, so the reservation works. Oh, okay. Do you want to check it? Okay. Hopefully, at least a good fraction of you are able to submit jobs. I guess I can. Okay. Okay. I see a lot of people wanting jobs, so that's good. Um, so jobs are written into this log file with 5. You should see something like this in that log file. It just kind of tells you all the configurations that you used, kind of defines the model here, and it starts a train. So this first configuration is the slowest configuration. I think it takes like a minute to finish every epoch. But in the README, we've also kind of screenshotted what you should be seeing in terms of performance. If you run this to convergence using the whole data set, it would take you 22 hours to train on this data set. Obviously, nobody has 22 hours, so I suggest that you copy this, which is basically a training run that we already did for you a while back because it takes 22 hours, and kind of paste it into your terminal. And we are going to be using TensorBoard to actually visualize things. Okay, so hopefully everyone is at the same position I'm in. So you've won the job, and you've also copied these 2 lines, which is going to copy a training run that we have done for you, which takes 22 hours. It's too slow to do, but at least you can visualize how the loss landscape looks like. In order to do that, we're going to use TensorBoard. So if you go to your file browser, you will see this Jupyter notebook called start_TensorBoard. Okay, so you want to open that and run this. So let's do that. And if it's not running for some reason, you also want to make sure that you're using the TensorFlow kernel, which should default to on top, but if it's not, you can change that. What this will do is it'll give you an address that you can click, and that's going to open TensorBoard for you. Okay. So I have 2 jobs here. One is something that I copied, which is the base training job if you're drawn into convergence, and the short one. It's too big. The way I like to visualize stuff in TensorBoard is you just go to scalar. You can set the smoothing to 0, so it gives you the raw data. And then you can look at different ones here and toggle between them to see the performance. And there's different metrics that we are tracking over the entire training. Okay, so is everybody able to open the TensorBoard? Oh, okay, sorry. Okay, I'll stop here and make sure everyone is at least copied the example logs and is able to open TensorBoard. And if anyone's having issues, just raise your hand and we will come around. Raise your hand if you're having trouble. Okay. Welcome back to the flow. Okay, it seems like most people, at least where I am, if you want to look at images, you would go to the images tab, and that'll kind of show you what we are predicting. So that's the target. That's like a atmospheric variable, and this is what the vision transformer is predicting in this training run. Okay, and then you can kind of toggle between the steps to see different images, and that's how the prediction has been evolving in training time. Okay. Okay, we'll wait for those people who are still stuck. That's right. Yeah. And it's also like ground samples, so we can actually do faster. Okay, I think. Let me know. Okay. Okay, so performance with that single shot configuration is going to look something like this. It's going to say time taken for one epoch is like 8 seconds. Sorry, yeah, 61 seconds with an average sample rate of 8 samples per second. On average, you will see that the throughput achieved is 8.8 samples. So in the last slide, I was talking about how you want to improve your I/O performance, and you can do that by just increasing the number of workers. So in the next job submission, what we're going to do is we're going to use this argument num data workers, and you can put it to any value of your choice, and increase that number so that you can get faster throughput just on the I/O side. So let's go ahead, copy that. I'm going to go back to my terminal. Oops. Paste that. So the job that I've screenshotted is using 8 data workers, but you could use like 4 or 2 or 16 and just see what happens. So we're going to set 8 data workers. This run num argument just basically labels the configuration so that 2 configurations don't clash when you're visualizing the results in TensorBoard. Okay, so we're going to submit this job. Okay, and that's gone. Just gonna wait for it to start. But in the meantime, we've kind of copied what the result will look like. You will see that at least on the NVIDIA GPU, if we use 8 data workers, the sample rate slowly increases from like 8.8 to about like 11 to 12 samples per second, which is pretty decent. But at some point, you will see diminishing returns because your CPU is trying to feed data fast enough into the GPU. If you're doing more complicated things, once again, I've linked the NVIDIA DALI library here, which helps you do some more overlap between the feeding of data into the GPU and GPU computation itself. And the last thing, once again, these are just like instructive examples. We kind of recommend that you switch these on by default. For transformers, mixed position training is going to be super important. Um, there's some things that NVIDIA GPUs automatically do for you. They actually use a precision called TF32, which is a little similar to FP32, but reduced precision to already take advantage of tensor cores. And these are enabled for you by default. But if you want to see what happens if you don't have it, you can set this environment variable to 0, and it will not use those, and you will see a slight decrease in performance. So before, if I had like 11 seconds, or sorry, 11 samples per second, it will drop to like 9 samples per second because the TF32 acceleration is not used. But just in the interest of time, you can now switch on mixed position by setting this amp mode to be FP16. You can also set it to BF16 if you want. That's just a different data type. And once again, you just name the run number. So let's go ahead and submit that as well. Actually, the previous one is still running. And I'm going to submit the FP16 run as well. Okay. Hopefully, people are still able to submit to the batch queue. I'm currently at this part of the README where we're using AMP on Perlmutter to use mixed position. And what you will see if you use mixed position is that, so the job is still running, but this is the screenshot of what you will see. The average samples per second jumps from like 12 samples to like 37 or 38 samples per second. So already just by switching on mixed position, you will see like a really big acceleration, only because the transformer model is very compute bound. It has large matrix multiplies, and if you effectively use tensor cores, you can get a pretty big performance boost. You will see something very similar to BF16. BF16 usually is slightly faster than FP16 because it doesn't do all the scaling and rescaling business. But that's something that you can play around with. There are some stability concerns whether you use FP16 or BF16, and that's completely empirical. At least for this tutorial, we're going to stick to FP16. Okay. So let's go back and see if anything ran. So once again, all the outputs are named as VIT/LFI/single GPU with your job ID. And you can open any of them to actually see whatever we've screenshotted in the README. Okay, so this is the FP16 run. It's still running. Actually, let me tail it. And what you can see is that it's like 35 or 36 samples per second, roughly. And that's almost like 3 times faster than without FP16. Okay. Is everyone roughly at the same spot where I am? Is anybody still lagging behind or needs any sort of help? Okay. Okay, good. And the last optimization flag that we're going to switch on is JIT compilation. This is done by just wrapping the model in tosh.compile. There's a few other things I didn't talk about, like your optimizer actually does a bunch of operations as well. Like if we're using the Atom optimizer here, kind of compute things like momentum and variance of your gradients. It's good to fuse all these operations into a single kernel. Again, the story is same. If you're using PyTorch, when you call an optimizer, there's just a flag called fused. You can just set that to true, and it will call the fused optimizer by default underneath the hood. So that's what we have done. So if you actually go into the code like train.py and see what each of these flags does, I'm actually going to go back to my terminal. And open my train function. And I'm going to search for enable JIT. So the first thing that will do is it'll wrap your model in tosh.compile. So model equals tosh.compile of model. So one line change. And for optimizer, what it'll do is it'll take this fused parameter and set it. So those are the only 2 changes. And if you actually go ahead and submit that job, Once again, you can just copy that from here, submit that. What you should see is the throughput now increases to like 41 to 42 samples per second. It may not seem like much to you, but in reality, the number of samples you have is like hundreds of thousands. So even like a 20% or 10% increase is still going to be useful to you in terms of end-to-end training time. So, but if your data set is not that big, maybe you won't see that many benefits. Okay. Okay, so this was just super quick, just to show you that with simple flags, if you just turn them on, then you can see some performance advantages. You can also see all the same things in TensorBoard. So if you go back to scalars and I'm just gonna move this, and you can always click the reload button here, and it will just reload with all the configs that it's running. So just going to switch everything off. So I had JIT, FP16, and NW8. Okay, so I mean, the loss curves don't change. These are purely performance. So you will still see the same training and validation loss. Sorry. Oh, I should mention that this RMSC U10M on valid means that it's a validation root mean squared error of predicting U10 meters. That's like the velocity at elevation of 10 meters over the entire globe. And we're just computing the RMSC component. And same as before, you can always, oops. Yeah, sorry. You can always go to the images section and kind of see what's going on in your predictions. Okay. So let's go back to scalars and let's go to average samples per second. And what you can see is that there's a big performance boost by coming from your baseline with 8 data workers and just going to FP16 mixed position. This is a different way to visualize the same results. Okay. And this is average samples in time. Okay. I suggest you don't submit this last configuration because it's, again, super slow. It takes like an hour or something to run. We don't have that kind of time. But this is what happens if I use a single GPU, switch on all the optimization configurations, and then just submit it on the full data set. So which for this data set in this example has 30,000 samples. So which is actually 1/10 of the data sets they actually use to pre-train these models. And if you submit this, I think it takes a few hours to actually come to a reasonable convergence point. You can do this later if you want, but we've kind of showed you how the training curve is going to look like for that configuration in this image. So you should be able to see that in the future as well. Okay, so that was just a single GPU optimization section. So we're ready to go to distributing our training with data parallelism. For that, we're going to use a different submit script. It's called submit_dataparallel.sh. There's no reason for you to switch submit scripts, but just to make it easy for you to understand the differences. If you actually go into that, you'll automatically see that we've set these flags called n tasks per node as 4, CPUs per task as 32, and GPUs per node as 4. That's because Perlmutter has 4 GPUs per node. And when you're doing distributed data parallel training, you want to make sure each GPU has its own task. So if you're using 4 GPUs, you want 4 tasks. Using 32 GPUs, you want 3 tasks. Okay. Okay, let's actually submit a data parallel one. So we're now going to use a full node, which is 4 GPUs, and we're going to increase our batch size from 16 to 64. The idea is that as your batch size grows, you should be able to train faster. The ideal scaling is if you increase batch size 4 times, then your training performance should be 4 times faster. But as I mentioned in the talk, there's some communication costs like all reduce. These typically get overlapped. So you should still see somewhere close to 4x performance, but it might be like 3 point something in general. So let's go ahead and submit this job. So this is going to submit dataparallel.sh. It's going to submit the config PS64 opt. If you want to understand what that config is, once again, if you go back to config width and go down, you will just see that in BS64 opt, we're going to set the global batch size to 64. And really important, we're going to scale the learning rate. As the batch size grows, we're going to keep increasing the learning rate as a square root of how fast the batch size is changing, okay? All right, so let's do that. Okay. I'm going to wait until everyone submitted the data palette one. Anyone having issues? Good. Okay, so this is going to take a little bit of time. I think it takes a few minutes to do an epoch, but at least hopefully people's jobs are starting. Um, the way distributed data palette works is really simple. So we have this script called export ddp.was.sh. There's actually no reason to do it separately. I kind of separated it out here for you so you explicitly know how we set environment variables. So if you go into this file, it's called vim export ddp.was.sh. You'll see that we have exported the following environment variables. It's going to use the slurm proc ID, which is a slurm variable, to find the rank of your GPU, your local rank, and the world size. Is everybody seeing this file? It's called export ddp.was.sh. If you're in Jupyter, then that would be up here. You can just double click that. This is to let DDP know that you're setting like local ranks, the number of GPUs using Slurm variables because we're using Slurm to submit the jobs. And in this case, since we're using 4 GPUs, we'll have your world size is going to be 4. Your local rank is either going to be 0, 1, 2, 3, depending on which GPU you're on, and so is your world rank. Okay. And if you go back to, yeah. That's right. Exactly. Yeah. So DDP needs these variables to be set up so that it knows how many GPUs you're using and what rank you're on. And if you go into your train script, which is just train.py, you will actually see in the bottom that the only change we make to the model is that we wrap that model in distributed data parallel. This local rank comes from environment variables. So let me just show you how that works. Oh, sorry, this is train.py. So once again, you go into Jupyter, it's called train.py, and you can open it. And this is your entire train function, okay? Okay, so if you go to the bottom of this file, we've kind of asked for environment variables like world size and set that based on what export DDP underscore was actually setting. So world size is coming from Slurm. Once again, that's 4 GPUs in this example. Your local rank is, again, Slurm tells PyTorch which local rank you're on, 0, 1, 2, 3. And the third thing you want to be careful about, but honestly, DDP will automatically do it for you if you're doing nothing else and just data parallelism, is to set how many data shards that you want. It's equal to your world size, and which data shard ID you're on, which is just equal to your rank. So it's just telling that's just to tell the data loader that I'm going to be using 4 GPUs, so split my data into 4 GPUs, and it also tells the data loader which index I'm on, so it knows which GPU to send which batch shard to. So for that, you can look at utils dataloader.py, and in the slides, I kind of mentioned that you would be using distributed sampler. So that's getting called here, and we're going to just set the number of shards and your rank in the distributed sampler to be your world size and your world rank. Okay, so the flow is you first get environment variables set up from Slurm. You tell PyTorch DDP that I'm going to be using this many GPUs and this is my local rank. And then in my data loader, I'm going to tell distributed sampler that I have this many model replicas, and once again, this is my local rank. Yeah. Right. Um, if you're doing just data parallelism, then it's equal to world size. If you're doing model parallelism, you're going to need to tell PyTorch to create communicator groups. So we'll come to that in the next section. So yeah, you just have to tell PyTorch that there's going to be this many data parallel groups. It's just another simple utility that we've implemented for you. Yeah, we'll get that for the model parallel section. Yeah. Our local rank is just in that node. There's 4 GPUs, so 0, 1, 2, 3, 4, and then world rank is 0, 1, 2, 3, 4, 5, 6, 7, 8, so on if I use 64 GPUs. So, okay, if I had 64 GPUs, let's say I'm the 63rd GPU, my world rank is going to be 62, but my local rank is in that node, I would probably just be the third GPU. That'll be 2. It's just because we have this concept of nodes, and it's not like all the GPUs are just connected in like a single array. There's 4 GPUs in a node, and then nodes are connected. So you, it's only, yeah, I mean, you need to pass it to DDP. The data, the data loader only cares about world size and world rank. And the place where that's implemented is in this utils data loader. Within your data loader, I'm setting the number of replicas. That's a distributed sampler flag that just tells the sampler that I have this many model replicas. So in data parallelism, you're always copying the model, which is equal to the world size in this case, and what the rank is, which is the world rank. The reason why what happens underneath the hood is, so you have a big batch. If I know how many replicas there are, distributed sampler will just split it up into that many splits, and then it'll give the 0th split to the 0th GPU, first split to the first GPU, and that's why it needs to rank. So if you're on GPU number 4, it'll take the 4th split and then just send it to the GPU for processing. Okay, let's see if the if the job actually started. Okay, it's running. All the data parallel runs is kind of flagged with this data parallel in the output file. Let's first make sure that people are able to run the data parallel job. So you can do 3 types of jobs. Honestly, you can do whatever you want, but we don't want to flood the reservation. So okay, yeah. So okay, you can do whatever you want. Okay, so okay. Yeah, so the first script here is really going to run 1 node, so 4 GPUs. The second 2 is going to use 4 nodes, so 16 GPUs, and we're going to scale the batch size to 256. And the last one is actually going to scale the batch size to 1024 and use 64 GPUs to do data parallel scaling. So let's actually submit all of them. If everybody submits 16 node jobs, we might. Okay, let's see. Okay, so I submitted it, and go ahead and submit some data parallel jobs, and then we'll see in the training logs how the training curves are progressing, and we also want to keep track of throughput and sample rate. Okay, so we'll stop here and just now it's more like free running. We'll come back to the model parallel section where we're going to make the model bigger, overflow the GPU memory, and use tensor parallel to shard it. But let's first finish the data parallelism. What? Raise your hands. Oh, yeah. If there's any issues, we'll be roaming around. Yeah, so you do S cancel your job ID. I'm not going to cancel anything.
Technical question, then, yeah.
Oh, sure.
It's a hard question. Yeah, I'll take the easy question.
You don't have to. But okay, good. One job is to. They're all running on it. Nobody's, you want to get. Okay, okay, but you're typical GPU runs will share. All the data out of one. All those things. Good. That's the different now. You just don't want to use both. That one I literally went to find out. Oh, okay. Yeah, actually. Yeah, right now, with by the GDP, how many days will fix it? They're looking at pretty well. I feel like people still look at other tutorials, but still not completely. Only model algorithm is a little bit slow. I would say not that yet. It's still haven't provided configured that takes up and work, but then move it to later. Yeah. Oh no. I mentioned it yet. It's not going to be just.
Should I tell people that?
Take an hour.
Oh, we're going to go. No, that's well, there's already. Oh, okay. Once they get the number. Oh.
Everyone running, people being stuck like a car running go because they're waiting. Quite a bit better. Yeah, there's one that has to be
faster something but it was same mistake, but we treated the most great like so what's that optimizer there? So there's also an advantage here. There's grab and scaling instead. In that case, well, by definition, it's not only so you want to accelerate the
And then you haven't finished all the data parallel stuff. Forward. Does anybody finish the data parallel examples? One person, one winner. Good job. You didn't make those prizes related to that. That could be you didn't read anything. Just kind of fix that. challenge questions, right? You have a question.
Right. Are they still on? Look like a ring like plastic. I've probably never even gone to the get for this one. What's the URL? Oh, it's gonna say DL4Sci that that. Good, good, just get in line with the.
DL4Sci.
Yeah. Did Shashank cover any of the things you want?
Well,
Like this, some of the, this one. You talk about it? What about this one?
and it's also like kind of depends on how you submit it, right? Because if you use for
Oh, DDP is independent of the launcher, right?
oh, sorry. I thought you were looking at this one. But this one didn't know.
Why do we want this additional links? It just engages them as a
Yeah, but if there's something like that, okay, so did anyone finish the data parallel right? And so were you able to see some output, like the relative speed on sensor board or just in the log? Yeah, but that's like the final roll. Okay, are you gonna cover the?
Yeah.
We need to switch it up.
A thing? Should I do that?
Yeah, I'm just going to show the results first. What do I got, right?
Okay, quick question to people to see how if they understood some key things in the material. So you're doing like data parallel examples now, right? So we're running models on many GPUs in a data parallel way, a kind of synchronized way. There are kind of two things that have to happen in the pipeline or in the code in order to ensure that this works so that all these models actually train together. Can anybody tell me what those two things are? or one of them. I don't know if I asked that as clearly as I could have. Huh? Right. There are sort of two ingredients that have to happen in order for data parallel training for models. We have copies of models across different GPUs, right? How do we ensure that they're actually all kind of working together? And I mean, you can say anything that comes to your mind really about this. What's necessary about it? And I can guide the answers. Syncing is along the lines. What do we need to? What kind of synchronization do we need to do? All reduce of what? The gradients, and we do this at every iteration, right? Great. So is that all we need, or is there anything else that happens to happen like at the start? Huh? Initialize the communicator. Yeah, so technically you have to initialize libraries for communication, but I'm thinking more like algorithmically or tell how many GPUs. Yeah, but I'm still looking for one other thing. Yeah, you have to be on the training allocation. Okay. We always do like a random initialization of the model weights, right? So what do we have to do to make sure things work correctly? Yeah, right. And so I think there's something in the README a question about why we do a broadcast of the weights at the start. I don't know if Shashank covered something about that, but like when you construct a DDP wrapper around your model, that will do a broadcast call to make sure every GPU starts with the same model, and then the all reduce step ensures that everybody at every step has the same copy of the weights. That make sense? Okay, good job.
Okay. This might take some time to run, but hopefully at the end of the day, you see something like this screenshot here. The baseline model is running on one GPU, and this on the x-axis is the amount of time it takes to run. It's pretty slow. It only reaches convergence at several hours. Whereas if you keep increasing the batch size, things should go faster. But as you can see here, the curves start to come closer to each other. The 16 optimized version is still good, but still not great. You can go faster with 256 or 1024. But at some point, you're getting diminishing returns. That's actually because you don't have enough data in your training data set to actually keep increasing batch size. So that's what I was talking about in the lectures. Data parallel scaling is not infinite. You will hit a wall at some point only because there's not enough variability in your data set. There might be like correlations. And at some point, all those assumptions about having IID samples from your training distribution break down. Okay, so in this specific example, it's totally useless for you to do batch size 1024 because it gives you pretty much, it goes much faster, but it converges slower than batch size 256 and 64. So at the end of the day, you should have just picked batch size 64 or 256. Okay, I do want to spend some time on the model parallel section because this is the section that is typically more advanced, but you don't find good documentations on how things work. So the idea here is that we want to use larger models. So that's either like bigger weight matrices, or it can even be like higher resolution data sets. But the problem is that they will inflate your memory consumption, and at some point, they're not going to fit in the GPU. So we need to parallelize further. So I talked about orchestration. All that logic is actually in this file, utils/com.py. But once again, I'm going to go through the basic idea. So we're interested in having orthogonal GPU groups. So here's like a quick example in the README. So I'm just reading through here. Let's say I have 8 GPUs in total, and I want to do 4-way tensor parallelism and 2-way data parallelism. The logic that you have to implement in your code is that your tensor parallel group should be GPUs number 0, 1, 2, 3, and 4, 5, 6, 7. And your data parallel will always be in the orthogonal dimension. So it's going to be 0 and 4, 1 and 5, 2 and 6, and 3 and 7, and so on. Okay, so you can think of it as a rectangular grid The first like row dimension is the tensor parallel, and the column dimension is the data parallel. And if we had more dimensions, it just starts becoming like a hyperrectangle. There is this function here. It's called check_rank generator. So if you go back to your Jupyter notebook, into utils, I think this works. So, and just run this notebook. Okay, I don't know what that syntax warning is. Okay, what it should give you is how this rank generator function is designing this hyperrectangle. Okay, so here's an example. So if I ask this rank generator, I'm going to use 32 GPUs. I'm going to ask it for 4-way tensor parallelism and 8-way data parallelism. So in total, I have 8 times 4 GPUs. It's going to tell me what my tensor parallel groups need to be. So tensor parallel groups are 0, 1, 2, 3, 4, 5, 6, 7, blah, blah, blah. And data parallel groups are always in the orthogonal dimension. So it's going to look like 0, 4, 8, 12, 16, 20, and so on. And then 1, 5, 9, 13, 17, and so on. What does this mean? It means that, let's say I'm GPU number 10 in this graph. Then GPU number 10 is going to do all the tensor parallel reductions only within its own group, which is GPUs 8, 9, 10, 11. So in PyTorch, you would just tell torch distributed, listen, I'm in this group with 8, 9, 10, 11 GPUs, and I'm going to do all my all reduces only within this group. Similarly, for that same GPU, it's going to look at my data parallel group, and it sees that in that group, there's GPU number 2, 6, 14, so on until 30. There's 8-way data parallelism, and it's going to do the wgrad all reduce only within this group. Does that make sense? Any questions there? Okay, you can play around with this, switch it to something else. I don't know, 16. It'll create tensor parallel, data parallel groups. It has other stuff too it can do. If you want to do like context parallel on top of that, it'll create like even more groups. But can someone tell me why the tensor parallel groups are closest together? I kind of went over this in the lectures. So there's 2 ways to do this. I can either keep the data parallel GPUs closest together, or I can keep the tensor parallel GPUs close together. Does anybody remember why? Yes. Yeah, that's right. Yeah. Okay, yeah. So, okay. The question is, in this figure here, or result, the tensor parallel GPUs are close together. So the group number 1 has 0, 1, 2, 3. Group number 2 has 4, 5, 6, 7. I didn't have to design this way. I could have had tensor parallel GPUs to be 0, 7, 15, so on, like far apart from each other. And the data parallel groups are far apart from each other, 0, 4, which means they're actually physically far apart. And the reason, as was correctly mentioned, is that tensor parallelism is more communication heavy. It happens in every layer with those all reduces that you want to do for the activations. And so you want to keep them as close as possible. And in Perlmutter, 4 GPUs on the node are connected with NVLink. NVLink is a fast bandwidth technology that gives you roughly like 10x the bandwidth between only those 4 GPUs. So you want to make sure all your communication heavy functions are all close together. So that's what this order thing does. It tells the rank generator which GPUs to place first. So it's telling the generator, place the tensor parallel GPUs before the context parallel pipeline data parallel. Okay, if you switch this up, you will see different things. Okay, so so this function is implemented in the code, and this notebook is only to show you how things work, and so you're familiar with the hyperrectangle terminology. The train function for model parallelism is actually a separate training function. You don't have to keep it separate, but the reason why it's separate is so you can clearly see the differences, and that's called train_MP. MP just stands for model parallel. So if we actually open that up and go down, you will see very, very slight differences. You're going to have things like your batch size only split across data parallel GPUs. So for example, here, your local batch size is global batch size divided by the size of your data parallel. So what com.getSize will do is it'll go to those groups it'll go to each data parallel, that list, and it'll just query the length of that list. Okay, so in that example, this is going to be 8. Even though you're using like 32 GPUs, you only want 8-way data parallelism, so you want to split your batch 8 ways. And once again, to your data loader, what you will tell it is, don't use all 32 GPUs, only use the size of the data parallel groups, which is 8 in this case, and only get the rank in the data parallel group, right? So once again, what that means is, if I'm in, let's say, the first data parallel group, the ranks here are 0, 1, 2, 3, and so on and so forth, even though that's not the global rank. So the utilities are all implemented for you, so hopefully it's clear that what's happening underneath the hood. Okay, let's go back to the README, and you can spend time afterwards to also see how things work. There's a bit of text here to show you everything that I talked about in the slides, like how do you build custom AutoGrad functions, have links to where it's actually implemented. Like if we just click one of these and go down, you will see these things like copy to parallel region. That's what I was talking about when you want to implement your custom model reduces. And you can also see how it's kind of integrated into the model. And to actually see the effect of model parallelism, what we're going to do now is we're going to run a different configuration. It's called MP, stands for model parallel. And for this, we're going to increase the vision transformer size from 384, that was the original embedding dimension, to 1536, which is 4 times. What happens is now your model is actually 16 times bigger, only because your weight matrix looks something like E cross F. F is typically 4 times C, so it scales quadratically with E. So if you increase something 4 times, it's going to be 16. So now the model is actually super big, and it's not going to fit in GPU. So if you actually go ahead and submit this job, let me do that. And here, this argument tensor parallel just means how many GPUs I'm going to use for model parallel. I'm going to set it to 1 here to force it to not do model parallelism. You're going to see something that looks like this in your log files. It's going to say torch out of memory, error, CUDA out of memory, try to allocate something. GPU has total capacity of 39.39 GB. What it means is that the model was too big and all the memory that you needed is not actually there on the GPU. So that job will actually fail and will actually crash with this out of memory signal. It turns out that Perlmutter has 80 gig GPUs, which we're not using for this reservation. But you could submit outside the reservation to the 80 gig nodes in specific. And if you actually do that, what you will see is, so I'm also tracking the memory usage using like PyTorch memory. You can actually see that that memory uses 53, okay, roughly like 54, 55 gigabytes on the HBM. So if I had a 40 gig node, then it's going to overflow the memory. Okay. And then what you can do is you can actually submit the tensor parallel version, which is going to use 4-way tensor parallel. Just to make sure everyone's on the same page, I'm still going to do the same batch size. So I'm going to use batch size of 64. So I'm going to use 4 GPUs to shard the batches. And I'm also going to use 4-way tensor parallel. So in total, I'm going to need 16 GPUs. Hopefully that's clear. So what that means on Perlmutter is I'm going to submit this job with 4 nodes. Each node has 4 GPUs. So in total, I'm going to request 16 GPUs, only because I'm doing both 4-way data parallel and 4-way model parallel simultaneously. Okay, so let's run that as well. Maybe let's do this here. The tensor parallel runs also take a little bit of time, like 10 minutes per epoch. It's actually because this is actually a very big model. And even though we've reduced the data set size, it still takes some time to get something that looks reasonable. But you can just leave your jobs running and come back and check the logs. Once again, we've copied what happens. And what you should be seeing is something like memory reduction is now gone all the way down to like 38 gigs, which is good. You've reduced the memory. But another thing is, so your throughput, if I had used just 1 GPU, is like 51 samples per second. And your throughput also needs to increase if you're using model parallelism, because the second reason to do model parallelism is just to make things go faster. More GPUs means more compute, so you want things to go faster. And if you go back to your tensor board, you should see something like the model parallel runs are always giving you lower RMSEs compared to your data parallel runs. And that's because we're using a bigger model. And that's generally the reason to go to bigger models. More capacity to learn, more approximation capabilities, and you should be seeing better RMSEs. Okay. So you can play around and like submit jobs and see how things are going. But I think we're actually running out of time. It's almost like 12:20 now.
Did you kill the reservation?
I won. Yeah. So reservation will go until once your jobs will still be running. Yeah. Yeah, it doesn't matter. The jobs will go. You can come back, check the logs, and even after the reservation, you can submit to the normal queue. So in order to do that, you have to remove the reservation flag. So for that, you can go to any of these submit scripts. So for example, this is the data parallel submit scripts. There's a flag here that says reservation. You just like delete that line. I actually didn't go through this too much, but as I said before, we're using our entire software ecosystem is through containers. So there's no like module loads or pip installs that you have to do. So hopefully that should transfer directly. Okay. I don't think we'll have time to talk about context parallel, but if you're interested, okay, if your use case has really large inputs, then come and talk to me afterwards, and I can tell you a little bit about context parallel. So in this case, this is going to be really helpful. If you actually run this job, it's going to go even faster than the tensor parallel. And that's actually because context parallel is some kind of data parallelism. It's actually your data, your activation maps that's getting sharded across multiple GPUs. And once again, you have all those benefits where you can overlap some of that communication with computation. And in general, you will see that the throughput for that model for this parallelization one is pretty fast. Okay. There's a lot more useful links in the README. So this entire thing is designed so that you can go home and read it at your own leisure. It's pretty detailed. I also have like links to Megatron here, which is the frontier library that NVIDIA uses to train language models. They have some pretty nice explanations. And if you understood how things work in the slides, then you will see very similar things in these libraries as well. For the last few minutes, I know that there were some people who are talking to us about getting compute access on NERSC and how we can engage with people. So for that, we actually have a NERSC staff member, Johannes, who is right at the back, who's going to tell you a little bit about some like call for proposals so that you get to engage with NERSC folk. Yeah, this will be super quick, and then we can go to lunch. Thanks. Yes. Do you want me to pull something up?
I was gonna, like, if you go back to your browser, yeah, I was gonna pull up the NESAP website.
Okay, let me do that.
Oh, right.
Okay.
Yeah.
We'll also post this on Slack, so you don't have
Right.
to know these links. Okay.
Yeah. So hi everyone. I wanted to make sure that this is on everyone's radar. If you just Google NERSC NESAP, NESAP stands for NERSC Science Acceleration Program. So now I think everyone can remember that NESAP as an acronym. But if you just Google NERSC NESAP, you'll find this website. And oops. Okay, and it's on Slack already. And what it does is it describes the NESAP program itself and some, highlights about the NERSC 10, also Doubtner system, and then a bunch of reasons why you might want to actually work with NESAP. We only list the Perlmutter compute resources. That's because in 2025 and 2026, we won't actually have Doubtner available, but then in 2027, Doubtner will be available for early access. And this is another thing that NESAP gets you. So basically when you say 5,000 hours in 2025, 10,000 hours in 2026, there's like an unknown number of hours depending on how early access goes that's available in 2027 as well for Doubtner. So basically it's a program that allows you to get NERSC hours and access to NERSC staff and preferential access to hackathons. And really all you need to do to apply is you can follow the link down here in the blue box, and which should take you to a Google. Okay. You need at least a Google account to fill out the Google form. However, you know, I'm not going to log in as Shashank now. It's a fairly simple form. It's not like a proposal for research grant or something like that. It should take you an afternoon to fill out. So it's not a huge amount of work. So I encourage as many folks here as possible that think that they might be users on Doubtner. I highly encourage you to fill this out. And if you've got any questions, if you go to this other box down here, that shouldn't require login. Yes. So there are 2 more office hours available, and so you can drop in to these office hours to ask any questions you might have, or email me nesap@lbl.gov. That's actually listed up here. If you email this email address, you can ask questions about NESAP. And so in terms of eligibility, it's anyone who is a potential user of the Doubtner system. So you don't have to be a current NERSC user to apply for this. And yeah, I'm also around for questions, and I'm going to be giving a tour, so you can plenty of opportunity to ask me questions. All right, thank you very much.
For the tour, I think we added Friday people on the, yeah, so,
Oh, I'll get out of the way.
okay. What time?
Well, the tour, I will be walking over with folks as soon as we leave, I guess.
Okay, yeah, so you can meet in front. Other people can go for lunch and coffee. So you can do that or whatever. But if you are running stuff on this and you have questions, please,
By the way, all of these other NERSC people can also answer questions about NESAP.
Right.
Right. Oh, okay.
I know what I'm